Okay, for part 3 of the section on GPU acceleration, I'm going to be presenting the GPU Streamlines package. I want to mention that this package is not one I personally worked on, but I'm presenting it on behalf of the rest of the DIPY team and some collaborators at NVIDIA. It's a probabilistic tractography implementation on the GPU. It's available in this repository under the DIPY organization. The implementation itself is in C++, and it's using CMake for the build system. That's a popular cross-platform build tool for C++ projects. And it then generates Python wrappers using PyBind 11, which is a popular way of wrapping C++ code. And compilation of this tool requires that you have NVIDIA's CUDA toolkit and a compatible GPU. So you'll need to install that toolkit if you don't already have it. You can follow the instructions at NVIDIA's site for whichever platform you're on. This package, as I mentioned, is developed in a collaboration between NVIDIA, a number of people from, I think it's their HPC team, and as well as these academic sites. And the algorithm itself that's implemented is a residual bootstrap algorithm of Berman et al. 2008 Neuroimage publication. And this corresponds to the one in DIPY that if you use the boot direction getter with local tracker. And in the Streamlines package, the class for this is just called GPU tracker. And it has two primary methods, generate streamlines, and then there's a dump streamlines that can speed up saving those to disk. So to get a sense of how to call that on the GPU or how to modify an existing CPU script to work on the GPU, you can look at these two files basically that are included in the GPU Streamline repository, which are doing the same analysis, but one purely in DIPY and one that still runs the initial kind of model fitting in DIPY, but then does the tracking in the GPU Streamlines package. So that's a good example to get kind of oriented with how to apply this in practice. To install this package, we could reuse the same cuDIPY demo conda environment we created in part 2. The only things we need to add to that are we need to also install PyBind 11 and CMake so that those can be found when we're building the C++ project. And when you clone this repository, you'll also need to recurse submodules so that some of the PyBind 11 code gets included there. So once you've cloned that repository, you just navigate into that folder, run the installation script via bash, and then it will be installed into a subfolder called install. So if you navigate to that folder, you'll find the binary as well as these example, these two scripts and a couple others that will be in that folder. And so the only issue I had when trying this out was that my GPU was a little bit older than what's assumed in the CMake files packaged with GPU Streamlines, and I had to go in and add a specific flag to CMake telling it my card had a compute capability of 6.1. So there's this minus d CUDA compute capability equals 6.1 flag added to the CMake call. And if your card has compute capability at least 7, I don't think you'll need to edit anything in that script. But if you're on an older card, you may need to look up your compute capability and add it there. And you can find out these compute capabilities looking on NVIDIA's site for whatever GPU you have in your system. So I mentioned there are example scripts for generating streamlines. Those have to be called with appropriate command line arguments, and some detailed examples of those are given in the README that are in that repository. So in terms of the performance, it's quite impressive relative to the CPU implementation. Even with one GPU, we're seeing here for a pretty large task where we have a Hardy data set where we're running 27 seeds per white matter voxel. We're getting about a 200-fold speed up running this large data set in 250 seconds on one GPU, and this time decreases as we increase the number of GPUs used. And so it's actually a multi-GPU implementation, so it can distribute work across multiple GPUs in one workstation. And so in this case, we have 8 GPUs, and in that case, you get additional speed up to almost a factor 700 relative to the CPU case. And this is just a visual output of a subset of those streamlines that were created. I think 8 million are shown here out of the total 150 million that were generated for this 0.625 millimeter data set. So that's all I have for that section. So I would encourage you all to check out the GPU Streamlines repository, the cuDIPY repository, look at the examples that are there. And then there is basically the other few IPython notebooks I generated for this talk that have some kind of basic orientation things. And if you have questions, I'll be happy to entertain those on Friday. Thank you.